Hi, good morning. In this session, we will be discussing about the index, the different types of indexes, how to create the indexes and how to view the indexes in the data dictionary. Let us start with the introduction about indexes, then we move on to the types of indexes and then how to create different types of indexes, and then after creating the indexes, how do we see those indexes from the data dictionary view. At the end, we will be looking into alter the indexes and dropping the indexes. See, we have already seen in our earlier session what is index, the importance of index, and then some of the basic types of indexes. In this session, since it is advanced topics on SQL, we will be looking into all the different types of indexes, variety of indexes what we have in Oracle database till the latest version, and how do we create them, how do we see them from the data dictionary. Let us have introduction on index. Index is a database object. All the indexes will be stored in the database. User underscore indexes or user underscore ind underscore columns. These are the two main data dictionary views where the information about indexes will be stored. Some information will be available in user indexes and some more information will be available in user in columns, data dictionary views. The indexes can be created on columns of tables, either single column or multiple columns. That means one index can be created either on a single column or one index can be created on more than one column. When we create index on multiple columns, which is more than one column, that is one different type of index, that is called as composite index. There is a limit for the number of columns when we use multiple columns while creating the index. That we will see under composite index, what is the limit and what are the advantages of using composite index. Generally, the indexes will play a major role in improvement of the performance. See, normally when we do not have index on the tables and when we reference these tables in our queries, that is select statements or update statements or delete statements, then the performance will be slow, because when we do not have indexes on these tables, the database will go for full table scan. Full table scan is always costly than index scan. That is why the performance will be worst when we do not have indexes on the columns of tables, what we are referencing in the queries. Now, when we have indexes on the tables and when we reference these tables in our queries, then the database will not go for full table scan. The compiler will be using index scans. There are different types of index scans. This we will be discussing in our performance tuning sessions. What are the types of table access and index access methods and join methods. Those access methods we will be looking into in detail in our performance tuning sessions. So as of now, we will be using the term index scan. That means index scan is possible when we have index on the table in the sense on the column of a table or multiple columns of a table. So in that case the compiler uses index scan instead of full table scan. So when the compiler is using or optimizer is using the index scan instead of full table scan, the performance will be improved. The response time of the query will be improved. It could be select statement or update statement or delete statement. So even updates becomes faster. Not only the queries, not only the select statements, the updates become faster when we use index scan. Even the deletes become faster when we use index scans. So how the performance will be improved when we use index scan instead of table scan or full table scan, will be looking in our practical sessions when we do the performance tuning sessions. So now when we have indexes on the columns of table, then the optimizer will be using index scan so that the performance of the queries will be improved. Even updates and deletes or merge statements as well. How the performance will be improved when the optimizer uses index scan instead of full table scan. So full table scan is nothing but scanning the entire table, all the records of the table. After scanning the entire table, then it will decide what are the records eligible. But when we have index, it will go for index scan. When it is using index scan, it will use the row IDs internally. Row ID is a pseudo column which we have discussed in detail in our row ID topic. So we can see the in-depth knowledge on row ID in our row ID session. So internally index scan uses the row ID, which is the physical address of the actual record. So when it uses row ID, it exactly go to the physical location of that particular row and then it will bring it instead of scanning the entire table. That is why the index scan is always faster than full table scan. That is why we advise to use indexes on the tables or on the columns of tables in which those columns are frequently used in our queries. So whichever the columns are frequently used for searching in the conditional clauses of queries, on those columns we will be creating indexes. The type of index doesn't matter, but we need index. But when it comes to the performance, sometimes the type of index also matters. Based on the different situations, different scenarios, or based on the requirement, we will be creating different types of indexes on those columns. Let us see different types of indexes we have in Oracle database till the latest version. At higher level, we can differentiate all the indexes into two categories: B-tree indexes and bitmap indexes. Bitmap indexes were brought from data warehousing into our OLTP system. So at higher level, B-tree and bitmap. So most of the indexes will be falling under B-tree indexes, and bitmap is the different type of index. So when it comes to the types of indexes, we have B-tree index, normal index. The normal index is also called as regular index or non-unique index, or we can also call this as global index. B-tree index, first one. Second one is normal or regular or non-unique or global. This is second type of index. Next, unique index, composite index. Composite index is also called as concatenated index, bitmap index, bitmap join index, function based normal index, function based bitmap index. Both are function based indexes. So when it comes to the bitmap, three types of bitmap indexes are there: bitmap normal, bitmap join, bitmap function based. And when it comes to the function based normal and function based bitmap. Reverse key index, ascending index, descending index, global index, local index. These two indexes can be created on partitioned tables. Global index and local index can be created on partitioned tables only on partitioned tables. Global index can be created on normal also. Normal or partitioned tables, but local indexes can be created only on partitioned tables. Clustered index, IoT, index organized table, compressed index, invisible index, sort or no sort indexes, unusable index, virtual or no segment index. Actually, sort index is one, no sort index is another one, unusable index, virtual or no segment index. Virtual index or no segment index, both are same. So totally we have 21 different types of indexes in Oracle database up to the latest version. So let us see this list once again: B-tree index, normal index, unique index, composite index, bitmap index, bitmap join index, function based normal index, function based bitmap index, reverse key index, ascending index, descending index, global index, local index, clustered index, index organized table, compressed index, invisible index, sort index, no sort index, unusable index, virtual index or no segment index. These are the different types of indexes we have in Oracle database. Now let us see one by one in detail the brief introduction about all these indexes. Then we will go for the practical session, how do we create them. B-tree index. This is binary tree index. This is the full form, binary tree index. This binary tree can be balanced or unbalanced. The binary tree index can be balanced or unbalanced. It can be balanced binary tree index or unbalanced binary tree index. What is balanced, what is unbalanced? That we will see at the end of this session. Normal index. This is non-unique index. So, on columns of tables we just create index without specifying any type, that is normal index, also called as non-unique index or regular index, or we can also call this as global index. Means one index for the entire table. Entire table in the sense entire column of the table. Unique index. Normal index can be created on any type of column. It could be number, character, varchar, date, timestamp, etc. There are some limitations on special data types like raw, long, long raw, LOBs, B file, etc. Apart from that, on basic data types, we can create the normal index without any restriction. The column can have null values, the column can have duplicate values, still normal index can be created. Unique index. Unique index can be created on columns where the column does not have any duplicate values. If the column is not having any duplicate values, on such type of columns we can create unique indexes. The column can have duplicate values, but column can have null values, but duplicate values should not be present in case of unique index. If the column has duplicate values, we cannot create unique index on such type of columns. Composite index. One index on more than one column, one index on multiple columns. Normally indexes will be created on single column. So when we create the index on more than one column, then such type of indexes are called as composite index. When we create composite index, definitely we will be using minimum 2 columns or more than that. But there is a limit here. The maximum number of columns allowed for composite index is 32. We cannot have more than 32 columns in the composite index. If you try to use more than 32 columns, it will throw an error. So maximum number of columns allowed for composite index is 32 only. Now when we create a composite index, the column which is placed in the first position, the first or the leftmost column, topmost column, is called as leading column. Rest all other columns are called as non-leading columns. The first column of the composite index is called as leading column. All subsequent columns of the composite index is called as non-leading columns. There is an importance for leading column. If we use leading column in where clause of queries, then the index will be properly utilized and results will be proper. When we use non-leading columns of composite index in where clauses, then the index may not be utilized properly. Sometimes it will use, but most of the times it may not be used if we use non-leading columns of composite index in the where clause. Even though there is an index on that column, but still indexes may not be used sometimes. In that case, we have to force the indexes using compiler hints. We will discuss what is compiler hints, how to use the compiler hints, and how to force the index using compiler hint in our compiler hints session. So as of now, when we use non-leading columns of composite index, index may be used or may not be used. If it is not used, then we have to force it. How do we force it? Using compiler hint. But when we use leading column of composite index, definitely the index will always be used properly. Next, bitmap index. Bitmap indexes will be used on columns where the cardinality is very low. What is cardinality? Cardinality is nothing but the number of distinct values in the column. The column can have any number of values, but when we take the distinct number of values, that is called as cardinality. And when the cardinality is very low, that means when the column is having less number of distinct values, on such type of columns we use bitmap index. So when we create bitmap index, bitmap segments will be created internally, and each segment will have one value of that particular column. Let us take an example. Gender. The table will have billions of rows, but when we take the distinct values, it will have only 2, male or female. Department number, the number of rows are millions or billions, but when we take the distinct department numbers, maybe limited, maybe 10 or maybe 100. Manager, number of rows are more, but the distinct managers are, not all the employees are managers, very few employees are managers, so number of managers are limited. On such type of columns we create bitmap index because the cardinality is low. That means the number of distinct values in that particular column is smaller, is lesser. On such type of columns we go for bitmap indexes. Bitmap join index. While creating the bitmap index, we will be using a join condition. Means we will be joining 2 tables. With that join condition, we will be creating bitmap index on any one of the column. That type of index is called as bitmap join index. Because we are using join while creating the index, we call it as bitmap join index. Function based index, function based normal index. When we create an index, if we use any function or any expression with the column or columns, that index is called as function based index. Since we are using a function or an expression while creating the index becomes function based index. Generally, when we create an index on, let us take an example of ename column, employee name. We have created normal index on ename column. If we search based on where ename equal to ABCD, in that case the index will be properly utilized. It will go for index scan. Instead of that, if we use upper of ename equal to capital ABCD, even though index is present on ename column, because we are using a function to that column, index will be invalidated. That is why, since we know that we always search e-names in uppercase, so we are converting the e-name column to upper always in our search conditions. Instead of creating normal index in this case, we can go for function based index. Since we are always referencing ename as upper of ename, let us create the index using upper of ename itself. Now, whenever we use upper of ename, since index is present with the same function upper of ename, index will be properly utilized. Since there is a function, this index is called as function based index. It can be an expression also. Take another example, sal plus commission. If we create a composite index on salary comma commission, index is there on 2 different columns, but when we reference in the where clause, like where sal plus commission is greater than 5,000, in that case index will not be used. Either composite index on both the columns or individual indexes on these 2 columns, the indexes will not be used because we are using this as an expression. So instead of creating composite index or normal indexes, let us create function based index on the entire expression, function based index on sal plus commission, because this is how we are referencing in our where clause always. This is also a function based index. Function based bitmap index. We are creating bitmap index, but when we are creating a bitmap index, if we use any function with that becomes function based bitmap index. Suppose gender, we are creating bitmap index on gender. Now instead of using the gender column directly, if we use upper of gender, since we are creating bitmap index and with a function, that becomes function based bitmap index. Reverse key index. when we create an index, a copy of the indexed column will be copied into index segment along with row IDs. That means the data will be present in data segment as well as index segment for these two columns, for the column on which we have created the index. Only the indexed columns data will be copied into index segment. Rest all other columns data will be present in data segment. Means data segment will have the data of all the columns of that particular table, and when we create index on one column, that particular column's data will be copied from data segment to index segment. So this column's data is available in two segments now, data segment as well as index segment. But when the database server is copying the data from data segment to index segment, mostly the data will be sorted in ascending order. Now when we create reverse key index, instead of copying the data as it is, it will copy the data by reversing the data of each value. That means when we have ABCD as a value, when we create reverse key index, when it is copying ABCD value into index segment, it will be copied as DCBEA. It will be stored as DCBA. That means by reversing the value, each value of that particular column will be reversed. So in which situation we go for reverse key index? Take an example. We have the data like ABC1, ABC2, ABC3. In that case, if we create index, normal index, then it will store the data as ABC1, ABC2, ABC3. If we create reverse key index, then it will reverse the values and then it will store 1 CBA, CBA, 3 CBA, like that. Now when it is going for index scan, suppose if it is going for index range scan, it has to scan the first character, second character, third character and then fourth character to differentiate if it is in the normal order ABC1, ABC2, ABC3. In this case, for all the values, first character is same, second is same, third is same, fourth one differs. Instead of that, if we reverse it, the first character itself is different, so that the range scans will be faster. So in that case we go for reverse key index. Ascending index, this is the default option. By default, data will be sorted in ascending order. If at all you want to sort the data in the index segment in descending order, then we go for descending index. While creating the index, if you specify ascending or descending option along with column, then that type of index becomes ascending index or descending index. Ascending index is default option, we need not specify anything. But if at all you want in descending order, then we can specify descending index. Sometimes we may need both ascending and descending also. On first column we want ascending, second column we want descending. So we are searching for the data and at the end we are specifying the order by clause, column 1 ascending, column 2 descending. So when we perform this, if you create normal index in this case, so what happens is it will fetch the data based on index into the memory and then it will go for sorting. It has to sort in ascending order based on the first column and descending order based on the second column for the common values in the first column. Instead of that, if we would have created ascending and descending index on these two columns, like while creating the index, we are creating the composite index now. While creating the composite index, column 1 ascending, comma column 2 descending. If we create the index like this, in this case what happens is the data will be sorted in this particular order and stored in the index segment. Column 1 data will be in ascending order, column 2 data will be descending order for the common values of first column. So now when we select these two columns, column 1 comma column 2, and when we wanted to display the order in sorted order like ascending and descending, if we have ascending and descending index, the additional sorting can be avoided. Directly it can fetch from the table and display to us without doing sorting every time, because while storing the data itself it is sorting, so it is one time job, and whenever we select it need not go for sorting. So we will be saving a lot of time in performance, in response time, because we are avoiding the sorting. Sorting is costly for the performance, especially when we have high volume of data. So we require lot of memory space and it will take very long time. So when we have ascending and descending index, since we are avoiding the sorting at the end, we are simply dumping the data from index segment to buffer or memory, the performance becomes very fast. We will see this in our practical sessions, how to create them, and we will see practically how it will improve the performance in our performance tuning sessions. With each type of index we will see how the performance will be improved. Global index and local index. Global index can be created on normal table as well as partitioned table. That means one index for the entire table. But local indexes can be created only for partitioned tables. That means this local index will be treated as one index for each partition, even though there is single index on the entire column of the table, but for each partition this will be treated as a separate index automatically by the database server. Next, clustered index. And one advantage of using local index is when we search for a particular value, the optimizer will identify that this value is present in this particular partition,